In this video, we will introduce our paper, named NerVE. Given a point cloud, the problem is how to extract all its feature edges in the form of parametric curves. Previous works develop various pointwise features and estimate edge point saliency. However, their results could be noisy and incomplete, making the parametric curve extraction fail or have bad results. We propose a new edge representation, NerVE, for the edge extraction from point clouds. NerVE is fully compatible with the volumetric learning frameworks and can be easily converted to general piecewise linear curves, abbreviated with PWL curves. With the predicted PWL curves, the following parametric extraction can be greatly simplified to a graph search problem. Our method is evaluated on the ABC dataset. It outperforms others both qualitatively and quantitatively. In the area of CAD, reverse engineering, which aims to fully restore a CAD model from the input like point cloud, can benefit a wide range of applications like 3D modeling and industrial design. Thus, how to extract parametric curves from the input becomes a crucial step in this problem. The recently released ABC dataset provides a huge amount of CAD models. These models are known to be the boundary representation, which consists of vertex, edge, and face while satisfying certain topological constraints. For the edge, mostly used edge types are line, circle, B-spline, and so on. Currently, there are many off-the-shelf fitting algorithms for a certain curve type. Therefore, what is challenging is to discover the edge structure in the input point cloud. Previous methods commonly detect edge points as the first step by using different designs of pointwise features. Specifically, the traditional method VCM computes feature boundary by measuring Voronoi covariance. PIENet views edge detection as a pointwise classification. ECNet and DEF regress a point-to-edge distance field and discover edge points with small field values. However, the detected edge points can still be noisy and incomplete in some cases, which requires extra effort for post-processing and may result in failed reconstruction. Moreover, it is also difficult to figure out the edge structure in naturally unstructured points. For example, it requires accurate endpoint detection and correct connection relationship for curves. Edge points have to be simplified for fitting. And we usually need a special algorithm to handle the closed curves. All of these processes will affect the final results. So we are motivated to directly predict structured piecewise linear curves from a point cloud. The PWL curves can be regarded as a graph, which enables us to simplify these steps as operations on the graph. Endpoints can be found by degree, specifically, vertices with a degree larger than 2 are endpoints due to the BREP model constraint. Then connectivity between endpoints can be discovered by graph searching. No need for thinning. For closed curves, we only need to check all connected components. But it is not easy to represent a general piecewise linear curve in a learning framework, due to the high freedom nature of PWL curves. Here, we propose NerVE, a neural volumetric edge representation, fully compatible with a 3D learning framework and can easily transfer to PWL curves. Based on the predicted PWL curves, the parametric extraction process can be done efficiently and accurately. We first introduce the definition of NerVE. We define 3 attributes, i.e., edge occupancy, edge orientation, and edge point position in every regular cube grid. For the given curves, a cube is called occupied if it contains part of curves otherwise unoccupied. In an occupied cube, the edge orientation is defined as 3 binary values on 3 faces. A face is a value true if it is passed through by the curves. Next, point position P is defined in each occupied cube, which is usually the midpoint or endpoint of curves in the cube. In summary, NerVE is a cube grid with 7 values for each cube. 1 Boolean value for occupation, 3 Boolean values for orientation, and 3 float values for position. Here is a 2D illustration to convert NerVE to PWL curves. What we need is to do one thing repeatedly. If a face is true, then connect 2 points of the 2 cubes adjacent to the face. Assuming we already have predicted the PWL curve from the input point cloud, further parametric extraction can be done with the following steps. First, endpoints can be found by degree, then paths between endpoints or closed paths can be discovered by searching the graph. Finally, each path can be fitted, which usually turns out to be a least square problem and can be solved efficiently. We adopt 1 encoder and 3 decoders for NerVE learning. In the encoder part, pointwise features are extracted by a dense version of PointNet++. Then we apply average pooling and transform the pointwise features to cubewise features in the cube grid so that we can then use 3D convolution. Finally, we obtain a feature grid, with each cell having a feature vector. In the decoder part, 3 MLPs are used to predict 3 NerVE attributes of the cube using the feature in every cell. In addition, features of adjacent cubes are concatenated for the face status prediction. To avoid meaningless computation, we apply cube masks to the feature grid. In training, losses are only calculated in the filtered grid. For the experiment, we first compare NerVE with other methods for edge points estimation on the ABC dataset. The vertices of our predicted PWL curves are viewed as edge points. Chamfer distance and Hausdorff distance between edge points and ground truth edge samples are reported in the table. Our method outperforms others. For parametric curve extraction, we compare with DEF on their dataset DFSIM. Both numerical and visual results show our superiority. For the stress tests, our NerVE are more robust than other methods for inputs with different level of Gaussian noise and downsampling. Here are more visual results of our extracted parametric curves with their ground truth. It shows the ability of NerVE to represent general and complicated curves. Thank you for watching.